Once again, good morning. Today we're going to finish up Chapter 2. We started last class and did a review of really what we learned about the hydrogen atom from General Chemistry 1 last class, and the Rydberg formula, which I think you had a couple questions related to that on your homework that you just handed in. Today we'll be looking at electron configurations, again a review topic from your Chem 1 courses, but we're going to maybe give you a little further explanation or deeper explanation of why some of the little idiosyncrasies that you learn about in Chemistry 1, maybe you just had to memorize them back in that course, sort of what the underlying energetic principles are that govern that. And so that's really what's on tap for this morning. Okay. So we first want to talk about, or the next section to talk about, is what's known as the Aufbau Principle. Aufbau is just a German word that means the building up. Okay, so this explains how we build up electron configurations in atoms for multi-electron atoms. Again, as you progress through to other courses, in particular to PChem, you're going to learn that Schrodinger equation that we talked a little bit about last class can be solved exactly for the hydrogen atom or any other ion that has only one electron. And so we can exactly solve the math associated with that. But as soon as we get to 2 electrons, it's become too complex, even for the most advanced mathematicians, to exactly solve the Schrodinger equation for the energies of both electrons. Okay? But we learn important lessons from the hydrogen case that allow us to get really, really close or infer then what's happening for the 2 electron and up, 3 electron, 4 electrons. Okay? So the question then becomes, how do we arrange those electrons into the many different energy levels, sublevels, and individual orbitals that we talked about last class? And that's what the Aufbau principle is. Okay? So now ultimately the goal in distributing the electrons of an atom is to achieve the lowest total energy for the atom. The electrons, being negatively charged, wish to be drawn in close to the nucleus, which is positively charged. That is a low energy scenario. The further those electrons are away from the nucleus, the higher their energy is. So all of the electrons are competing to get in close to the nucleus. However, then there's another factor. They're too close to each other. And what you should have learned in a physics class is that like electric charges repel one another, and that raises their energy. Okay? And this idea of attraction and repulsion is going to be put to use in just a minute. Generally speaking, the way to accomplish this is if we add electrons to the lowest N plus L subshell available, we will accomplish this. Okay? And so by N plus L, I'm referring to the energy level plus the sublevel, the numerical value. So this explains why we have a 1s, 2s, 2p, 3s, 3p, and then why we have 4s before 3d, because the sum of N plus L is here 1, 2, 3, 3. The reason 2p is filled before 3s is that the lower n is filled first in any case where there's a tie between two n plus L values, right? And then 3p would have a 4, 4s would have a 4, but 3d has a 5. And so again, here's a tie. The lower n has been filled first. Now here, the 4s is actually a lower total than the 3d, and so we argue that it's going to have a lower total energy for the electron. And this system of n plus L can be used to continue this pattern so that you predict all of the orders. Okay? So that's, in general, that would be the way that you're adding electrons to the many different orbitals and sublevels of an atom. Another important consequence or factor to consider is what's known as the Pauli exclusion principle. The Pauli exclusion principle states that no two electrons in an atom can have an identical set of the four quantum numbers. The four quantum numbers, of course, being the n, the L, the m sub L, and then we didn't really talk about it the other day, but the m sub s, spin quantum number. The spin quantum number was not discovered or was not necessary in Schrodinger's and Heisenberg's work looking at hydrogen because there's only one electron. Spin isn't really a complicating factor until you have two electrons that may interact with each other, as it turns out. And there are only two possible spin values, plus or minus 1/2. As a consequence of that, because there are only two spin values, that means that an orbital can hold a single orbital, not a subshell, but an orbital can hold at most two electrons if those two electrons have opposite spins from one another. Right? And then you would have run out of unique quantum numbers to assign to an electron. If you try to put a third electron in there, it would need to have one of these two spins, so it would be identical to one of the others that's already there. And so by default, the orbital is then full with two electrons in it, we say. Okay? So this was sort of a restriction that was placed on this idea of building up atoms, all right, limiting how many you can have in any different orbital and sublevel. And then another interesting sort of premise or law, rule that was put forward was known as Hund's rule of maximum multiplicity. Okay. This rule stated that electrons, okay, align themselves in a given subshell with parallel spins in the different orbitals before pairing any electrons in one orbital of that subshell. The first element that sees this behavior, or that we can look at to sort of understand this, is carbon with 6 electrons. 1s2, 2s2, 2p2. the 2p energy level would have 3 orbitals. That would be part of it. They would be numbered -1, 0 to +1. All right. There are actually 3 possible ways that the 2 electrons could be added. 3 unique, let's say, ways that the electrons could be added to these orbitals. Okay. One case would put the 2 electrons together. So if Hund's rule was not known, okay, so let's pretend we didn't know this rule that I just laid out right here. We're going to justify why that rule is in place, in other words. Okay. One would be to spread the 2 electrons out in any 2 orbitals, okay, with the same spin. And one would be to spread the 2 electrons out in any 2 different orbitals with different spins. Okay. Now, it wouldn't matter if it's this orbital and this orbital, okay, or this one and this. That's the same configuration. All right, just 2 different orbitals. All right, same spin or different spin. And of course, we can't have 2 in the same orbital with the same spin. That would violate the Pauli exclusion principle then. All right, they would have the same numbers exactly to describe those 2 electrons. Okay, so the question that we want to look at here and basically re-arrive at Hund's rule of maximum multiplicity is which configuration or which arrangement has the lowest energy. Okay. In this first consideration, what we're looking at here is these 2 electrons. They experience a repulsive energy, which means it's positive or raises the energy of the atom, known as the Columbic energy of repulsion. The Columbic energy of repulsion. It's symbolized by the capital letter pi with a lowercase c. So that would raise, relative to an arbitrary, what we're going to call an arbitrary 0, that would raise the energy. Okay? Because these 2 electrons, what are they doing? They're negatively charged and they're sharing the same region of space. So they are going to be interacting with each other and pushing away from each other, out to get out of that space, in other words. Okay? And that's going to raise the energy of the atom. Okay? This second arrangement that we have here gives us another energetic interaction that we call the exchange energy. Okay, these 2 electrons have what we call an exchange energy, which lowers the total energy. So if I labeled this electron as electron 1 and this second one as electron 2, I could redraw this configuration with electron 2 in that first orbital and electron 1 in the second orbital. In other words, what I have done is swapped 2 of the electrons and arrived at the exact same configuration. This is the electrons are identical to one another, but they're in the nitty-gritty. You have to read the details, okay? If you want the particular details, they're in pages 27 and 28 is where all this is described, okay? If we get into the nitty-gritty of the math of the Schrodinger equation, it predicts that having the ability to exchange electrons like this, okay, in other words, multiple different electrons that could be in this first orbital, okay, but give you the same arrangement, is going to give you a net lowering of the energy. And so this energy is called the exchange energy, right? And so it's a lowering or a stabilizing. And here, in this third case, there are no repulsions and no exchanges. We cannot exchange these two electrons because they have different spins with one another. So you can only do this swapping if the other electron is just like you. All right? Those are sort of the rules. So here there are no exchanges and no repulsions. So this third case here serves as our 0 point, if you want. Okay, there's nothing affecting it. Okay, we could think of its energy, again, arbitrarily as 0. So if I consider now, I'm going to consider a scale of energy. Our three arrangements that we have, our up-down arrangement is going to be our arbitrary 0. Our up-up or down-down, but by convention we tend to use the up arrows first. Okay, and the book acknowledges that. That's just sort of an arbitrary rule. In reality, that's not necessarily true. A lone electron can have either a plus or a minus spin. Okay? And then, so this is lowered by the pi. Oops, I did not label it over here. We would call this exchange energy pi e. Okay? And it lowers, or it's a negative energy value then. Okay? So our middle case has been brought down. And then our upper case, or our first case, where we have the two electrons paired, has been increased by this pi c. Okay. So on the argument of these energetic interactions predicted by Schrodinger's equations, okay, the Hund's rule basically emerges. Atoms with parallel spins, their electrons spread out and the spins aligning, are going to be the lowest in energy, is what we see right here. And so that's known as Hund's rule of maximum multiplicity. Okay? So just to reinforce that, the arrangement with the electrons spread out and having all the same spin, that's what that word parallel would mean, right? Has the lowest energy. Okay. We'll do another example in a second, but let me pause and see if there's any questions about it so far, about this rule. Okay. All right, so let's work through a couple of the examples that are in the text, just to see if we can come up with the correct arrangements for any particular configuration that we might look at. Okay. Let's determine the correct configuration for oxygen. S22, S2, 2p4. So really what we need to look at is that 2p4 part. So you want to start just thinking about what are the possible ways that you could arrange 4 electrons. You could cram them all in like that, up, down, up, down. Okay. You could spread them all out and then come back with one down. You could try something like one pair and then the other two are not parallel aligned like that. Okay. If you flip this middle one, it will not give you a new arrangement then, by the way. That would be the same as this arrangement here. 3 in one direction and 1 in the opposite direction, right? Okay, so you want to think about that. This is 3 up, 1 down. This is 2 up, 2 down. Okay, so, and I don't think there are any other configurations that we could uniquely come up with for that. Anybody else think of any others? Nope, we got them all. Okay. So let's determine which of these is going to, or what the energetic contributions are for each of these. Okay. So in this case, we have 2 pi c's, because we have 2 pairs, each experiencing a Columbic repulsion. But we also have 2 pi e's, the 1-2 swap and the 3-4 swap. All right. So it's not all bad. There are 2 energetic repulsions which raise the energy, but then it would come back down a little bit. Now, in the grand scheme of things, the pi, I didn't draw it to scale necessarily here. The pi e's are not as significant as the pi c's. So it would be big 2 jumps up and then 2 little steps back down. All right, so this would still be from that arbitrary 0 starting point, would still be a raising of the energy. Okay? What do we have here? We have a pi c for the 1 pair that we have here. And then I'm going to label the 3 up spin arrows, 1, 2, 3. We have 1 and 2 could swap places. Okay, so these are going to be our pi. We're going to figure out how many pi e's we have. 1, 2. 1 and 3 could swap places. And 2 and 3 could swap places. So there are 3 pi e's there. And this is what is a stumbling block for folks. So if you don't get that, let me know. This is my chance to really explain to you what these exchanges are, since this is, I know, a new concept for students. All right. The down arrow we totally ignore because there's no other thing like it, right? You have to have another electron just like you with the same spin to consider the exchanges, these swaps. Okay. Now, in this third case, we again have a pi c. Okay. And now we can look at 1 and 2, and then I'm going to label 3 and 4 because those have the same spin. So our pi e's that we'd have would be a 1-2 swap, but I can't swap 1 with 3 or 4, and I can have a 3-4 swap. So I only get 2 pi e's in that case. So again, if you established an arbitrary 0 and had your energy here, the first arrangement would go up by 2 pi c's, okay? And then come back down. Let's make, you could choose whatever size you want, but just to exaggerate it, I'm going to choose these little arrows, okay? So here's where our first arrangement would be. Okay? Use enough ones. So we're going to call this arrangement A, arrangement B, arrangement C. Okay? Arrangement B would come up the 1 pi 1 and then back down 1, 2, 3. Okay? And then arrangement C would come back down just 2 of the pi e's, so it would be tucked in right there. So we see that B is the lowest energy. And B again has the maximum number of electrons with parallel spins that you can get. It's got 3 electrons with the same spin versus, in this case, having only 2. In either of these cases, having only 2 electrons with any one spin. Hund's rule of maximum multiplicity. That term multiplicity we don't use it so much in our work, but it is a term that gets used in PChem that refers to the number of unpaired electrons as well, which we'll care about a little bit later too, but not as much as you do in some PChem arguments. Okay, any questions then on that application there? All right, so this would allow you then to figure out the arrangement, the configuration of any atom, basically, how its last few electrons are spread out over the different orbitals of that valence energy level and subshell. Okay, but again, to remind us here, the first consideration is N plus L, lowest energy and sublevel combination. All right, and then these are much finer distinctions in energy that we're looking at here. This idea of the spins and spreading out the spins. Okay, so you wouldn't want to miss the big picture part first before you get to this. All right. Okay. The next topic that we want to look at then, which also relates to these concepts of the electron configurations, is the concept of shielding. And it explains some of the small oddities that occur in the electron configurations. Okay. So shielding is the phenomenon when inner, or what we sometimes refer to as the core electrons of an atom, block the nucleus from pulling on the outermost electrons of the atom. Okay. Just like it might get difficult for some of you who sit in the back rows to see certain things on the board, depending on where I'm positioned and where I'm writing, because there might be someone sitting right in front of you. You're partially shielded or obstructed from seeing that thing that I have written on the board. Okay? And so electrons experience a very similar phenomenon. When the innermost electrons are taking up as much of the space around the nucleus, making it harder for the outer electrons to feel that nucleus. So this creates what we call an effective nuclear charge. The effective nuclear charge is the number of protons that any electron feels or experiences based on its position in the atom. Okay? So the effective nuclear charge, Z star, is equal to Z minus S. So Z is the real nuclear charge, just the number of protons in the atom to begin with. And S is what's known as the shielding constant. Okay. Now, the shielding constants, there have been several different attempts to develop these, all in an effort to most accurately model sort of these known parameters of how So some people look at how hard it is to remove an electron from an atom, otherwise known as the ionization energy, right? So they use that property, and then they try to figure out, well, what must be going on with this shielding? And can we develop a system that predicts the amount of shielding that occurs? Somebody else might look at atomic radius. Somebody else might look at electron affinity. So different properties have been used to develop different scales. Right? What you need to realize anytime someone asks you to look up a value is to make sure you understand sort of what system it's based on. Right? There are different systems out there, as we're going to see when we talk about acids and bases, and so it's not quite as simple as just there being one answer to a question. All right? These are not theories, in other words, that have been predicted. These are an attempt to accurately explain what we know to already exist. All right? So it's almost backwards thinking to some extent. All right? So our book lays out one of the most commonly used sets of rules for coming up with the shielding constant. They're known as Slater's rules for shielding constants. S. Okay? I'm going to abbreviate them, but they are found on pages 30 and 32 of your textbook if you want the complete sort of full language, okay? And some examples that we're going to work through as well. Okay. So the first thing you need to do is a rearrangement of the electrons. All right, here's how you group the electrons. Your 1s electrons and your 2s, 2p are put together in a group. The parentheses are denoting groups. Okay? And then 3s and 3p are a group. 3d is a group. And then 4s and 4p. So that's your pattern. Your s and p always belong together. And then your d, and if you had it, as in the case of 4, f would go in there. And then you'd repeat this pattern, right? 5s, 5p, and on up. Okay, so I think that's enough for you to predict and understand the pattern. Okay. All right. Now this is not the order in which they are filled, but this is explained in the explanations here on pages 30 and 32. This is the order of which orbitals give the electrons the greatest probability of being close to the nucleus. Okay? If we look back, I think it's page, I wanted to bring up figures from the text today, but I think I have to renew my access to the textbook electronically, and I hadn't done that. Page 22 has a series of figures that come from the Schrodinger equation. So we glossed over some of this last class. But they describe the probability where it's most likely that you're going to find an electron in the different types of orbitals. Okay? And so what's kind of weird is, while we might fill the 4s before the 3d, an electron in the 3d actually has the opportunity or the probability to be closer to the nucleus. So in terms of thinking about who is blocking who, right, we have to think about this 3d then likely blocking the 4s if the odds tell us that it's closer to the nucleus than the 4s. Okay? All right? And so that's where this order was derived from, was those probability curves. Right, figuring out which electrons are likely to be closest to the nucleus. Okay? All right. Now, to develop the shielding constant then, here comes our set of rules here. Okay, first rule is pretty simple. Electrons, okay, to the right do not shield any electrons to their left. Okay. So in other words, the 4D cannot be shielding or blocking out the 4S, the 4P, the 3D. Okay. So you never have to worry about anything to your left. Okay. Or to your right. Okay. Sorry, you don't have to worry about any electrons to your right. Okay. All right. That's kind of obvious, but when you understand that order. Okay. All right. Rule 3. For an S or P electron, there are different rules for D's and F's. But first, for an S or P, okay, an electron in the same grouping as the electron of interest contributes 0.35 to S, the shielding constant. So that's part A. Okay. There's one exception to this. It's not worth memorizing. It's that if you were only looking at the 1s block, instead of 0.35, it's 0.3. We're not going to worry about that. We're going to look at larger ones. Okay. So if you were looking at just helium, it's the only case it would apply. Then you'd just use 0.3. Okay. What this number means is you can think of this 0.35 as if I'm an electron in this group right here, 2s, 2p. Every person in the same group as you, every person in the same row as you, is effectively blocking 35% of one proton. Okay? And that's because they're not like you guys sitting still. These electrons are moving around, right? And so if you all had to swarm around me, even though you guys are the front row, occasionally you might step in front of each other. And so 35% of the time, you can think of it as somebody in the same row as you is going to be in front of you. That's going to decrease your ability as a student to see me, as an electron to feel the protons that are in the nucleus. Okay, so that's what these decimals represent, is really what percentage of a proton is being blocked. Okay, so that's for electrons in the same group as us. Okay, now each electron in the n-1 grouping, okay, contributes 0.85 to S. Okay. So again, if I was an electron in the 3s, 3p grouping here, these guys in front of me, they're in front of me so much that they're each screening off or blocking off 85% of a proton from me. Okay? So I have to take that into account for every single electron in this group here. Okay? Then the last one, each electron in n-2 or lower, right? So if we're really far out away from the nucleus, we're going to have, significantly further down groups. So this would be part C. Each electron in an n-2 or lower group contributes 1.0 to S. So a full screening of a proton. Now, rule 4 will tell us what to do for a D or F electron. 4A is really the same as 3A. 0.35 per electron in the same group. Okay? So it's really the same. It diverges at B, though. Okay? Each electron to the left, so it doesn't matter, n minus 1 or n minus 2, contributes 1.0 to S. Okay? Again, there's a few more words with these rules on the pages that I've described here, but this is pretty much what you need to do. And we'll do a couple examples to lay it out for us as clear as possible. Okay. Any questions on them so far? Or, yeah, can't read something? Or?
For 3A, or no, 3B, you changed it to the right? Or no, it's 2. The one you said something about shielding it from the right.
Right, so what Rule 2 does is tells us if we're interested in what's happening here, 3S, 3P, we don't have to worry about anything to the right.
Oh,
Okay, it's kind of a weird way to say it. But this is kind of the language they use in the book. Electrons to the right of electron that you're interested in, do not shield anything to the left. Okay, yeah. So because what we're going to look at now is we're going to pick any random electron in an atom, not necessarily the last electron in an atom, right? And so if you're like the 20th electron in an atom that has 50 electrons, all those high energy electrons, they don't affect how you interact with the nucleus, only the low energy ones. That's kind of what Rule 2 is telling us here to do. Okay? Okay. Let's do a few of these examples then that are in the book. So again, they have us start with oxygen. Let's find the effective nuclear charge, Z star, for one of the 2p electrons in oxygen. So we would regroup our electrons to 1s2, 2s2, 2p4. Okay. Now, here's the first little, it's like, oh yeah, but it's the obvious thing that you got to do. So we are interested, right, in one of these electrons. So this group has 5 other electrons in it. You don't screen yourself, right? If you're a member of this group, you're not blocking your own ability to see the nucleus. Okay? It's just how many other electrons are in your group. So that's a classic little mistake that people make is they see 6 electrons in this group and they think 6 is the number that they're going to use to multiply, but there's only 5 other electrons because we're after one of them. Okay? Right. So really working from right to left, okay, even though we're used to reading from left to right, from right to left, we have 5 electrons times 0.35. Okay? Rule 3A. Each electron in the same group as us screens 0.35. Plus then 2 electrons at 0.85. The n-1 group, so n is 2 here, okay? n-1 group, so n is 1, contributes 0.85 per electron. Okay? So the shielding constant then is 1.75 plus 1.7, or 3.45. So the effective nuclear charge, oxygen's atomic number is 8 minus 3.45, so it's 4.55. So that's what we're saying is a 2p electron feels only 4.55 protons worth of nucleus in a hydrogen atom, or oxygen atom, rather than feeling the full 8 electrons that really are there. Okay, these 2p electrons feel 4.55. It would be the same for a 2s electron, by the way, because it's in the same group. All right, the probabilities tell us that the S and the P essentially are going to be shielding each other the same. All right, so if we redid this for the 2s, it would work out exactly the same. Okay, the other example, a little more involved here. We're going to look at nickel, and we're going to compare the effective nuclear charge for a 3d electron and 4s electron in nickel. So I'll pull the periodic table down for just a second so we can see where nickel is here. Okay, nickel is element 28. Everything would be normal to start. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then that would leave us with what appears to be a 3d8 configuration. So the groupings that we would have are 1s2, 2s2, 2p6, 3s2, 3p6, and then we do the 3d8 and the 4s2. Again, the concepts supported by experimental observations tell us that even though the 4s electrons give the nickel atom a lower energy, therefore they're filled before the 3ds, the 3d electrons are likely to be, the probability is that they're closer to the nucleus, so they are going to screen the 4s electrons. All right. So for the 3d electron, if we're looking at one electron in this group, we have 7 other electrons left over in that group times 0.35. Okay. And then for the D rules, which we still have over here, we don't have to worry about anything else. Now just everything to the left now contributes 1. So what's to the left of us? 8, 16, 18 electrons times 1.0. So you have 18 plus the 2.45, and so you get 20.45. So the effective nuclear charge is going to be 28 minus this 20.45, or 7.55. You could think of it as protons. Not really the unit, but I'm just trying to remind you that's what is effectively felt by 3D. Now for the 4s, the shielding constant would be, well, if we're looking at one of the 4s, that leaves 1 in that group, so you have 1 times 0.35. Okay. and then you go to the N-1 group. Now this is one of the few cases where it's sneaky, right? If N is 4, all of this is N-1. So even though they're written out in separate groups, they're all N-1. Okay, so you're just looking at what that first one is. So how many is that? That's 8 and 8, that's 16 times 0.85. And then what do we have left? We have 10 more in N-2 or lower, so that's 10 each at 1. Right? This would have been rule 3C. Each electron in N-2 or lower screens 1. Okay. So we get, let's see, 0.35 plus looks like 13.6 plus 10. This gives us a total screening of 23.95. So the effective nuclear charge is 28 minus that 23.95, or 4.05 protons. So what's the consequence? What are we looking at here? Okay? The 4s electron is held more weakly by the nickel atom and is thus likely to be removed before the 3d electron. So this concept of shielding and effective nuclear charge leads us directly into the properties, the periodic trends of many elements. Okay? We can use effective nuclear charge to predict the things like ionization energy, although it's kind of backwards, as I said. We had observed many, many ionization energies or atomic radii, electron affinities, and we used them to work backwards to these rules of Slater's rules, in this case, to predict what was going on with the interaction between a given electron and the nucleus of an atom. Okay? And those periodic trends are kind of what are described in the next several pages of the textbook. Right? Things that you again, learn a little bit about in your Chem 1 course. Right? Now, one other sort of interesting anomaly in electron configurations gets addressed here in this section of the chapter. But first, actually, before I go on, let me make sure everybody's okay with this and gets it. Yeah, question?
Where do you get the Z value?
The Z value is just the atomic number.
Okay.
Z is the symbol for atomic number, remember? So it's just whatever element's number you're looking at, that is the Z value. Yep. Never hurts to refresh the basics there. All right. So if you recall, when you learned a little bit about the periodic table and electron configurations in Chemistry 1, you may have learned about some cases where there were oddities in the order of adding electrons to transition metals in particular. The first place where this is most famously, pointed out and observed, okay, is usually right here with chromium. Okay, chromium, which has a total of 24 electrons, looks like it should have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4 configuration. But there is strong evidence that suggests the true configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5. And chromium is not the only element that has this sort of shifting of an electron. The most common explanation for this in a Chemistry 1 class, where your professor might ask you to memorize these or know about these, is that there's something about stability for this half shell, this half-filled shell, or in the case of copper doing this, to having a full D shell versus having 9 out of 10 positions filled. Okay, but now we can sort of acknowledge maybe a little bit more accurately what is happening here, or why this happens. Okay, and there are a couple of explanations for it. The one that I like the most is this pictorial version of what's going on with the energy levels. So on page 35, I'll attempt to draw this for us here. This is what I wanted to project. But on page 35, figure 2.12 shows us the relative energies of the orbitals. Okay, so this is what it's showing us. It shows the relative energies of the 4s and 3d orbitals. Okay, not so much the orbitals, but rather it's for an electron with the 2 different spins, or with each of the 2 spins. Okay, so there's 4 lines here. One set of lines looks roughly, they have a little curvature. It looks like that. And the other one runs parallel to it like this. So there's an energy scale here. Energy going up, energy going down. So this would be an electron with m sub s equal to -1/2 in a 4s orbital. The x-axis is atomic number. So as atomic number increases, as you move across this period, right? So this would start with potassium and calcium, scandium, vanadium, and then work its way across to copper and zinc to wrap this up, in other words. So you can think about the elements, or you can think about just what the atomic number is. Okay? What do we see here? We see here that the energy of the electron decreases. Okay? The energy is getting lower and lower. Okay? So that's good in terms of, these elements, they're electrons. What's happening here are they're getting closer and closer to the nucleus, because we know that atomic radius decreases as you slightly increase the protons and neutrons. That's a periodic trend. As you move across a row, atomic radius decreases, so the electrons are pulling closer to the protons. That's lowering the energy of the atom. Okay? So this is the S. So this is 4s with a -1/2. This is m sub s equals +1/2 in a 4s there. Okay? So what this shows us is, for potassium, the first electron goes here. For calcium, first electron goes here, the second electron goes here. Right? So you end up with a 4s1, a 4s2 configuration for calcium. All right? Now we need to see, where are the d orbitals? Okay? The d orbitals, I almost wish I had a different colored chalk here. Let me see if I do. see if this blue will show up better. If not, I'll go back to white. The d orbitals have a similar idea here. Now I got to get the curvature right. Okay. So they have a different slope, right? So these blue lines are the energies of electrons in the d orbitals. And again, you could be looking at a arbitrary, minus 1/2 spin and a plus 1/2 spin. So for scandium with 3 electrons, what you do is you just work your way up. The first electron, working your way up, the way to get the lowest energy, to put the first electron in the 4s. Then the next electron still in a 4s. And the next electron in a 3d. So this predicts a 4s2, 3d1. Okay? It's not until we get here to chromium where we get a 4s, then we hit a 3d, okay? And then we get back to 4p. Okay? So chromium is the first case. For chromium, what we see is that the 3d orbitals are lower in energy than not both, but than a second electron in 4s based on the pi c, pi e energies that we discussed earlier. Right? So when you consider that Coulombic repulsion energy, okay, and weigh it in to what's happening with these are mathematically predicted, these curves here, all right, from all that Schrodinger Equation stuff, all right. The long story made short is that we're going to, fill the 3D shell with 5 electrons before we add the second electron to 4s. And the other positions of overlap or of skipping, maybe not to scale on my picture here, but according to the picture in your book, okay, it's correctly labeled out, shows where these other places of skipping would occur. All right? And so there are a few cases. Let's see. Yeah, so copper, by the time you get out here to copper, this would be an example of copper. You'd have D5, then 1s, and then D5 again before you get back to having 4s too. All right? And zinc would be the same way. Okay? So this predicts for the third energy level. There's a similar set of calculations that could be made for the fourth and the fifth energy levels as well. All right? But our book just used it. And then the second half of this figure in the book is for these things as ions. What happens if we're ionizing an atom? And then things are a little bit different because, again, the order in is not the same as the order out. It doesn't just reverse. That's what the shielding examples showed us earlier. All right? While we may add electrons into a 3D first, 4s's are more shielded, so they're going to come out first. Same thing, some funny things are going to happen here. So you could look at a figure like this, and it would tell you which electrons would be the first to be taken out, okay, and then what electrons are left in the case of something being an ion, all right? Because what happens when you make these things ions is these slopes shift. So where the overlaps occur, is where the crisscrosses happen, are going to be in different positions, all right? If you change the angle of this set of orbitals here, they're not going to overlap at chromium. they're going to overlap maybe at scandium or out here at vanadium, okay, for the first time, all right, where these oddities in the electron configurations occur. All right? So if you ever sort of wondered why we had those 3d5s, or the book shows us all the elements that do that. Of course, this whole row here does it, and then it tends to be this row here that does it. And then palladium is an oddity as well. It has no s electrons and 4d10 electrons. So it's both of those lines would be overlapped, okay, before the two blue lines would be below the bottom white line in that figure in the case of palladium. Okay. So these are all predicted, or predictable, I should say now. We know the result, but they can now all be justified and predicted based on these calculations of what the energies of these different orbitals are. Okay. So again, all of this is used to understand how certain atoms behave. And the last bit of material in the chapter, I don't need to rehash it a whole lot, is just explaining ionization energy. So how much energy is involved to take away the first or second electron, usually, from an atom. There's another energy called the electron affinity. So this is the energy involved with adding an electron, or halogens in particular, right, and oxygen. These things at the right side, they desire to add electrons to their configurations, we know. And there's an energy exchange that occurs, or energy change that happens in those cases. And then the radii of atoms, which I've already alluded to. We know that there's a trend that size decreases as you move across a given period. Of course, size increases as you move down any one of the families because you're using the larger energy levels, and as n increases, the probability space, that sphere, has to increase with that n value as well. Okay, and that brings us really to the end of this second chapter that we have here. All right, so. A couple minutes, could be done a couple minutes early. That's fine with me, but I could also, answer any questions. I could go back and clarify anything from the lecture today. There's a homework assignment posted to Moodle, homework 2.2. All right, doing some of these configurations with the pi c, pi e arguments, and then doing some of the Slater's rules of determining the effective nuclear charge as well. All right. On Thursday, we will get into Chapter 3. Just to give you a heads up, we'll be looking at Lewis dot diagrams and resonance and formal charge. So a pretty quick review, again, of simple bonding theories as it's referred to in this text. All right. What took a whole chapter or so to learn in your Chem 1 course, we're going to review in a single day. All right. So with that, have a good rest of your day, and I'll see you then.